Today we shall begin with the numericals. Numerical number 5.3. Okay. A short bar magnet placed with the axis at 30 degree with the uniform magnetic field of 0.25 Tesla experiences a torque of magnitude 4.5 10 to the power minus 2 joule. What is the magnitude of magnetic moment of that magnet? Okay. Now we want to find out the magnetic moment. Okay. And torque is given to us, so it's very easy to understand. Okay. The formula which we are using is tau is equal to m cross b. Okay. Tau is equal to m cross b we shall use. Okay. Tau is equal to m cross b, and that will be equal to tau is equal to mb sin theta. So m will be equal to tau upon b sin theta. A value of torque is given. It is 4.5 10 to the power minus 2. So we can write 0.045 upon b is given 0.25, and sin 30 as you know it is 1 by 2. So you can simplify and you can get the answer of 0.36 ampere meter square. Okay. Now numerical number 5.4. A short bar magnet of magnetic moment 0.32 joule per Tesla is placed in a uniform magnetic field of 0.15 Tesla. If the bar is free to rotate in the plane of the field, which orientation would correspond to its stable and unstable equilibrium? What is the potential energy of the magnet in each case? Okay. Now stable equilibrium, as you know, when axis of bar magnet makes an angle theta is equal to 0. Okay. So for stable equilibrium, the angle between magnetic dipole moment and B, that is magnetic field, both must be parallel to each other, so theta will be equal to 0. And in this case, the potential energy U is equal to minus mb cos theta. So you can write minus mb cos 0. So this becomes minus m into b, and the value of m is given, that is 0.32. Magnetic field is given 0.15. Okay, just we have to simplify and you will get the minimum energy, which is the energy associated with most stable condition. Okay. Now for unstable equilibrium, theta will be equal to 180. Okay. So m and b are anti-parallel to each other, we can say. So u is equal to same equation mb cos theta, but theta we have to take 180, and cos 180, as you know, it is minus 1. So this value u will be equal to positive mb, the value which we have got earlier with positive sign. It will be, and this will be the maximum potential energy, and round about 0.048 joule. Okay. So this is for unstable equilibrium. Now numerical number 5.5. Closely wound solenoid of 800 turns and area of cross section 2.5 10 to the power minus 4 meter square. So area is given here. Okay, this is the number of turns. Okay, which carries electric current of 3.0 ampere. 3 ampere is the current. Explain the sense in which the solenoid acts like a bar magnet. How does it behave as a bar magnet? And we find the magnetic moment. Okay. Now, first of all, we shall find the magnetic moment, and magnetic moment of the solenoid is given by the formula. Say ms, I write for solenoid, it is n into I into a. Here a is a vector quantity, so this will also become the vector quantity. And if you write the values here, the number of turns, the current passing through it, and the value of area, I am writing just now. So this answer will be 0.6 ampere meter square. Now if you consider the solenoid this way, then the axis of solenoid is this. This is the axis of solenoid. And in the direction of the axis of solenoid, this magnetic moment will be, because area vector is in the direction of axis of solenoid. Now if you pass the current this way, okay, this is the direction of current, then if you curl your finger in this direction, okay, then the thumb will remain in this direction. So right now the magnetic moment, if you consider the current this way, if you take the opposite current, then the magnetic moment will be in this direction. Right now the current is taken in this particular direction, that is why the magnetic moment will be towards left. And similar explanation can be understood if this is a bar magnet, okay, then bar magnet will have this as a south pole and this as a north pole. Okay, right now if you look from this side, from left hand side, try to understand this way. If you have this solenoid and if the current is passed this way, okay, then if you look from this particular end of the solenoid, then the current is found to be moving in anti-clockwise direction. So this will behave as north pole and this will behave as a south pole. And the magnetic moment is from south to north. This way also it can be understood. And if you consider this as a bar of magnet or a bar magnet, then also this is south pole and this is north pole, and the direction of magnetic moment is from south to north. Okay, so if you consider this as a bar magnet, if you place as if a bar magnet here instead of the solenoid, okay, then this bar magnet will also have the magnetic moment in the same direction that of the solenoid. When you place the north pole of bar magnet towards right and south pole towards left. Okay, so the solenoid behaves like a bar magnet, having the same magnetic moment, that is magnetic moment of bar magnet same as that of the solenoid. Okay, so they both have quite similar magnetic field also. Okay, now numerical number 5.6. okay, if the solenoid in this exercise 5.5 is free to turn about the vertical direction and a uniform horizontal magnetic field is 0.25 Tesla is applied, what is the magnitude of torque on the solenoid when its axis makes an angle of 30 degree with the direction of applied field? Now we want to find out the torque which is acting. Okay, and as you know that torque is equal to m cross b, that is mb sin theta. So torque is equal to mb sin theta. Now solenoid is placed, okay, so I write ms just to specify that we are placing solenoid. Now this value of magnetic moment we got earlier 0.6, we have calculated in 5.5. magnetic field is 0.25 and angle is 30 degrees, so sin 30. Now just we have to multiply, sin 30 is 0.5 or 1 by 2 we can say. So you will get 0.075 Newton meter as torque, and direction of the torque it will be according to right hand screw rule. Okay, because torque is equal to M cross B. So direction of the torque can be found by having the cross product of this and direction of M cross B, which can be found by using the right hand screw rule, and it is along the direction of M cross B. Okay. Now we shall move further. Now example number 5.7, a bar magnet of magnetic moment. It is given 1.5 joule per Tesla lies aligned with the direction of uniform magnetic field. Okay, so alignment is there, theta will be equal to 0. Now what is the amount of work required by an external torque to turn the magnet so as to align its magnetic moment, that is normal to the field and opposite to the field direction? Then what is the torque on the magnet in these two cases? Okay. Now see, first of all, potential energy of the dipole, we know that it is given by U is equal to minus m dot B. Okay, U is equal to minus m dot B. Okay, and we can easily write U1 is equal to initial position, I write as U1. So minus m dot B, so mb cos theta, and it becomes minus mb cos theta 1, where theta 1 is the initial angle of magnetic moment with magnetic field. U2 is equal to minus mb cos theta 2. Now work done is nothing but final potential energy minus initial potential energy. So we can write minus mb cos theta 2 plus mb cos theta 1, and mb can be taken as common. It can be cos theta 1 minus cos theta 2. Now initial position of theta 1 is 0. Finally you want to take it at 90 degree. Magnetic moment makes an angle of 90 degree. So we can write here m is 1.5, the magnetic field is 0.22, and cos theta 1 initial position is the parallel magnetic moment with magnetic field. So cos 0 it becomes cos 0 minus final position is 90 degree, that of magnetic moment with magnetic field. So cos 90. Okay. Now you can simplify cos 0 is 1. So just we have to multiply these two terms, 1.5 into 0.22, and that will give you 0.33 joule amount of energy. Okay. Now the next is, now theta is given for the second requirement. What is the now torque? Torque we want to find out. Now torque when it is at 90 degree. Okay, we want to find out the torque, and as you know that torque is equal to mb sin theta. So we just have to place the value here, 1.5 into 0.22, and sin 90 is 1. So again 0.33 Newton meter will be the torque. Okay. Now when theta is 180, okay, second case we have opposite to the field. Opposite to the field means theta is equal to 180. This is the second case. Okay, when the angle between dipole moment and magnetic field is 180, then sin 180, here theta you write 180, sin 180 is 0. So torque acting will be equal to 0. Okay.